get started, let me first introduce you. Hello and welcome all again to um, the webinar series from the IEEE Sensors Council Optical Sensors Cluster. Uh, this is one of the talks within the series. We have already done, I believe, 3 talks, and we have had some excellent speakers, and we have an excellent lineup of speakers for the next almost a year. And we are very excited to welcome Dr. Fred Mokua Manuni, who will be speaking on ultrasensitive laser absorption spectroscopy for trace gas detection. And just a bit about the speaker. Dr. Manuni is a physicist and sustainability advocate with a focus on laser technology and environmental innovation. His background is in applied optics and lasers, and he's currently pursuing a master's in laser technology. He leads the strategic planning at Be Your Best, BYB, a youth-led platform promoting the sustainable development goals. And he's a founder of Youth Champions for the Sustainable Development Goals. His current research interests lie in green hydrogen and laser-based methods for environmental monitoring. He's been honored with several national and international recognitions for his work in youth leadership and scientific innovation. So beyond the research and beyond all the academics, the impact that he's making in the society, especially for the youth and training the next generation, has been wonderful. So we can't be more proud and excited to welcome Dr. Manuni, or Fred as we call, to come and speak and continue his to start his talk. So over to you, Fred. Thank you.
Okay, thank you, Dr. Ashwin. My name, as they have introduced, as Fred Mokua, and I work in an intersection of science, technology, and sustainable development. I have the passion in applying innovation to real world challenges, and often I focus on mental health and youth well-being. And today I want to share insight on another area I deeply care about the environment and health-focused technology, specifically on how we can detect gases in trace amounts using multi-pass optical cell. And this presentation will bring together physics, engineering, and public health applications. So I'll go to introduction of my presentation. And these are optical gas sensor. These are a very vital tool for gas trace detection. The multi-cells will enhance sensitivity via an extended light path, and its application include environmental monitoring and breath analysis. And in trace gases, even a small concentration can indicate various issues. And it is used to detect diseases, e.g. asthma, cancer, and also environmental pollution, and sometimes industrial leaks. The challenges is detecting them accurately and quickly, and maybe sometimes non-invasively. So these lesser based methods are emerging ideal due to their personal precision and portability. Trace gas detection is not just a lab exercise. It is a frontline tool in diagnosis of disease like cancer, monitoring of air quality, or detecting explosive material. Conventional method like gas chromatography are too slow and sometimes bulky. So if you use the optical technique, particularly less absorption spectroscopy, it will offer an uncontacted and highly sensitive solution. So we'll go to principle of multiple cell. This system will use laser absorption spectroscopy, LSA. Then the core physics is the Beer-Lambert law. And most of you know about it. The laser is tuned to a specific absorption line where the target gas absorbs most of the increasing the optical path length, boosts sensitivity. And as you see, every gas has a unique fingerprint on how it observes light at a different wavelength. So by tuning a laser to this fingerprint and measuring how light gets absorbed, we can calculate how much of that gas is present. And this principle is majorly used in lab and can be adapted to use in the field with multi-pass cells. Yeah. So we go to design of this multi-pass cell. Am I too fast? Hi.
Absolutely not.
Okay.
No, you're great. That's fine.
The design of the multiple pass cell. Then we use a mirror that reflect a laser beam through the gas samples multiple times. Then extend the path from centimeter of tenths or hundreds of meter. Then the design will include the Harriot cell, the white cell, and a circular or a schematic configuration. So I'll just explain the process. So if you might like imagine shining a laser beam between two mirrors. Instead of going through this sample once, the light bounces back and forth many times. Dramatically, it will increase the chances of interaction with the target gas, and this will make the detection more sensitive even when the concentration is extremely low. Yeah. So we go to simulation. So the simulation and beam pattern. So simulation tool you will use like the MUPAS GUI to calculate. So we'll use this to calculate the beam entry and exit angles, then the mirror tilt and separation. Also, we'll use to calculate the spot distribution and overlaps. This will ensure the beam stay within the bonds and hit the output all. It will hit the output all clearly. So when you align the system with mirrors and a laser is extremely delicate. That's why simulation tools are critical, and they will let us digitally test hundred of mirror configuration, beam angles, separation of optimized for maximum path length and stable beam pattern. So we go to matrix path length and path length will be up to 150 meter, and it is achievable in the compact cell. And then the high SNR enable the PPT to detect some limit. For example, 8 PPT detection of ethane with around 1.5 meter path. So in simulation, in gas detection, gas that will be detected will be ethane, especially the biomarker or oxidative stress. And in the methane, it will indicate the gut health. And for formaldehyde, it will detect the cancer risk. And if it is water vapor, it will detect the hydration and calibration. Yeah. Then the detection range will range from the PPT to PPB. So when you use this multipass system, we are able to detect event down to 80 ppt within 20 seconds. And this precise enough to real-time breath analysis. And this could help detect disease before symptoms appear. The same system can monitor environmental leak and outdoor quality. The system integration with components such as 3.8 nanometer tunable laser. Then you'll have a multiple cell of around 1.5 meter optical path. And then we have a PBSE photodetector. You'll have a lock-in amplifier for noise filtering. Then you'll have a pressure control software interface. So the laser detection and hardware are integrated into a compact setup. The signal modulation and averaging will help reduce the background noise. And a common issue, which is also a common issue in most of the optical system, the software will automate the tuning, control, and visualization, which will allow fast and repeatable measurement. So the performance metric will be sensitivity, linearity. In terms of the sensitivity, will be 80 pp2 for a 10. Linearity, it will be a stable from 1 ppb to 1 ppm. And then the stability will drift of less than 4% for around 3 days. And this multiple gas capacity, it will do a simultaneous detection possible. And then the response time will be less than 30 seconds for most of the typical gases. So the system sensitivity and precision are not just the lab results, they will be validated through repeatable testing. And this will make it suitable for medical, environment, and industrial application. It works without needing acyrogenic cooling or complex sample preps. Yeah. So the challenges of while I was doing this work was one, the alignment complexity, and then the fringe interference, which we can be referred as the optical noise, was another challenge. Then we had limited commercial availability of affordable multipass setup. Yeah. And then the future work I'm planning to do is I look for a portable device for breathing diagnosis. And I'll also work on AI integration for real-time decision making. Then I'll do the expansion to detect more volatile organic compound like VOSCS. And I'll ensure it is maybe battery operated or IoT enabled field sensor. So the current system that I've designed still require somehow careful configuration and alignment and maybe calibration, then reducing complexity and integration model electronics could democratize gas diagnosis. Like imagine a breathalyzer which will detect early cancer or chronic disease. The future will be working towards that. And in conclusion, these are multiple optical cell will dramatically enhance gas detection sensitivity. Then proven success in detecting critical biomarker. Then software and simulation that will simplify design and optimization. And future will lie of this project will lie in mini utilization and AI integration. For broader health monitoring. And then this work, as you have seen, it will showcase how physics and engineering will come together for health sustainability and from detecting pollutant to diagnosing disease from breath. And the potential application may be wide and more impactful. So thank you for your attention. I'm happy to take questions.
Great, thank you. I'd like to thank you first. And we're open for questions. We have sufficient amount of time. So any questions from the audience? Please feel free to unmute yourself and ask a question, or you can type your question on chat, and I will be happy to relay that. Maybe I can initiate the question if people are feeling shy to ask. Thank you for the wonderful talk, Fred. So when you talk about miniaturization, what is the like how portable it is right now? Is the setup more tabletop? Is it or a little more? Is it fairly heavy, or to what level of miniaturization is possible, and what are you looking at? Hello. Hello. You seem to be muted, Fred, in case you're talking.
Three. Maybe you come up with your question. Maybe I had an internet issue.
Okay, I can repeat my question. I was asking about, you mentioned miniaturization, so I wanted to understand what is the current setups? Is it how portable it is, and whether it's heavy, or how big is it, and what to the level of miniaturization you're targeting?
So the current setup is on the lab based. We do it at National Institute for Optic and Lasers, and it look more complex and user. So I'm planning to make a multipass gas detection that will be portable and handheld or wearable. And then I'm planning to integrate them into the smartphones or compact medical devices. Then I'll scale them to for drones or mobile environmental sensors. Yeah.
Sounds good.
Uh,
Thanks for that. Questions from the audience? Anyone? Looks like we don't have any questions at this point of time, Fred. Maybe if we get any question over email or they can reach out to you. We'd really like to thank you for your talk, and we do because we do this online. I was just trying to do a clap gesture. But thank you. Thank you for the wonderful talk and being part of this series. So we finish early, but that's great. Short and lovely talks are always helpful as well. Thank you. Have a great day.
okay, thank you.